Okay, so today's Saturday session has to do with thermodynamics and energetics. And so the first part we'll be doing is we will focus on the topic 5, SL, energetics. And we need to talk about a couple of fundamental things first before we kind of get into all the calculations and everything like that. And so what I like to do here, and since you've seen it already, this is a little bit of a revision, but we need to establish the main kind of contrast between the two following concepts, which is exothermic versus an endothermic process. I'm going to do this as kind of a 3-column chart here, and comparing and contrasting, because it's important that we understand everything relative to these two processes in a lot of different terms. Okay. And so the first and foremost is simply just the definition. An exothermic reaction is heat lost to the surroundings. An endothermic is heat gained from the surroundings. And it's important that we establish what system and surroundings are. And you need to remember that the system is just the chemical reaction alone, not the environment the chemical reaction is taking in, not anything surrounding the chemical reaction. It is simply just the particles that are involved in the chemical reaction. Okay? So just because you're doing a reaction in water, that doesn't make water part of the system, because the water is not reacting. It's just a medium. And so that's still part of the surroundings. Your hand, when you touch a beaker, is part of the surroundings. So you're feeling the surroundings aspect. The thermometer that measures the temperature is measuring the surroundings. Okay? And so that's another thing. And so when we talk about the temperature change, we're talking about the measurement of temperature of the surroundings always. You can never measure the temperature of the system. You're measuring how the surroundings respond to it. And so in an exothermic reaction, you should have a positive change in temperature. In an endothermic reaction, you should have a negative change in temperature. So if your final temperature is higher than your initial temperature, that is a sign of an exothermic reaction. Yes. The system itself, correct. There's no way to do it. No, because just by default, the thermometer itself is part of the surroundings. It's not involved in the reaction. So what it's measuring is the heat being released to the thermometer or the heat being taken away from the thermometer. That's what it's measuring. So it's always part of the surroundings in chemistry context. Okay. Let's see. Okay. Enthalpy change. Okay. So the change in heat content of the system. So how much energy is being exchanged from the system to the surroundings? Okay, and that's your delta H, enthalpy. And we'll spend a lot of time on calculating delta H in a little bit. For an exothermic reaction, you should have a delta H that's negative, because that's the delta H of the system. It's implied. Usually you don't write system as a subscript, but it's implied that it's always of the system, because it's releasing energy. In an endothermic reaction, the system should be gaining energy for the reaction to occur. Bless you. Okay. So enthalpy change, make sure you're kind of recognizing the signs for this, especially in HL, because when you get into Gibbs free energy and things like that, you'll have to be able to recognize signs to be able to determine whether it's spontaneous or not. Okay. The energy diagram. Okay, how we represent the energy of the reactants and the energy of the products in the system. So if we're talking about the heat content, and this is generally progress. It's not a time. It's just going from reactants to products. So don't think of this as like a time in unit. But in a exothermic reaction, your reactants start with a higher energy content, and the products end up with a lower energy content. Yes? Yeah. Okay. So the whole process, don't worry about the kind of whole activation energy that we talked about earlier. Really, all they're looking for here to represent exothermic is the change in heat content from the reactants to products. And this area right here is your delta H of the reaction. And conversely, your endothermic reaction should end up with a state that is higher in energy and heat content than the original reactants. Yes? That's the heat content, or the enthalpy. Yeah. So the internal, I shouldn't say internal, I gotta be careful. So the heat content of this system, the reactants, as it goes through the reaction and changing bonds, breaking and forming bonds, the products end up with a lower total heat content. And that energy is released in the form of delta H here. And this is still the energy that is absorbed by the system. You may also want to make a note that delta H is a state function. Okay, what I mean by a state function is that the pathway doesn't matter. The reactant energy and the product energy, the difference, no matter which way, which direction you go, if you start with a certain reactants and you end with certain products, your delta H will never change. Doesn't matter how many steps it goes through. It doesn't matter what catalysts and stuff like that. The delta H will never change. That's an important assumption that we make for any type of reaction, that we don't care about the pathway here. Stability of the reactants and products. So the energy state, essentially. Here, in an exothermic, the products are more stable than the reactants, because stability is inferred by the amount of energy required to stay in that state. So if the products require less energy to stay in that state, they're more stable. Okay. And conversely, on the endothermic, the reactants are more stable than the products, because you're having provided energy to actually react. Okay. Also in here, bond transformation. What type of bond process is happening with an exothermic versus endothermic reaction? An exothermic reaction is bond forming. Okay, when a bond forms, the reason why a bond forms is because it allows the two or more particles to have a lower energy state sharing electrons than when they're separate. It's the whole point of a bond. So when you form a bond, you release energy because the atoms have reached a state where it's lower energy state to share the electrons and have their own individual electrons. And therefore, endothermic reaction is bond breaking. I kind of relate this to kind of imagine like two magnets that represent a bond. If the magnets are stuck together, if you want to pull those magnets apart, you have to put energy into the system to separate those, keep those magnets apart. But if you have the magnets apart and you let them come together, they collide, and then there's usually a sound that's released. That sound is the energy that's released when they are now at a lower energy state. So bond forming is exothermic, bond breaking is endothermic. Now, every reaction has both of these things happening. So every reaction breaks bonds, every reaction forms bonds. The issue is the difference between how much energy the reaction is absorbing by breaking the bonds and then how much energy the system's releasing by forming the bonds. And that difference is your delta H. And we'll talk about how to calculate bond enthalpy a little bit later in this session. Yes. No, it's already in solution. Yeah. Okay. Questions about that? Okay. The first type of calculation for enthalpy, because there's a lot of different processes for enthalpy. I'm going to do this one first, is calorimetry. Okay. So calorimetry is the experimental procedure where you measure the change of T on a substance to determine your enthalpy change. Okay. So the whole point of calorimetry is you put the reaction in a medium that you can measure the temperature change of, and you know how much energy it takes to change the temperature of that medium, which then allows you to calculate that. And so what you have to know for this problem is you have to know what's called the specific heat capacity, okay, which is C. I guess lowercase c if you're really getting to it. Actually, no, it's heat capacity. So specific heat, bless you. Specific heat capacity is energy required to increase 1 gram of substance 1 degree Celsius. Okay. So for water in liquid form, that is 4.18 joules per gram degree Celsius or Kelvin. It doesn't really matter which unit of temperature in Celsius or Kelvin you use because we're looking at the difference in temperature. And the difference in temperature in Kelvin and Celsius is the same value. So it doesn't really matter. But so knowing that, what values do you need to know to be able to calculate the amount of energy that the water absorbed? What values do you need to know? Yes, Ashini. Okay, starting and ending temperature, right? Because the starting to ending temperature, TF minus TI, allows you to find the change in temperature. So that tells you how many degrees you had to heat up. Right. And what else do you need to know? Huh? The volume of what? The volume of the medium, right? Of, in this case, water. Okay. Now, you need to know the volume of the water. Now, that's not directly related to this equation, but there is a correlation there, because we know as a definition that 1 gram of water equals 1 centimeter cubed of water. That's the density of water. 1 gram of water is equal to 1 centimeter cubed of water. So if I measure the volume of water as 50 centimeters cubed, that's the equivalent of 50 grams. And so knowing these two values allows us to use specific heat capacity to calculate the amount of energy. And so these are the two things that you need to measure to do that, because a constant is specifically designed to multiply and divide by values to get you a number. It's a given, a defined value. And so this constant then leads to the equation that you're probably familiar with, which is Q equals mc delta T, which is what we just explained up here using the units of specific heat capacity. You have to know the mass of the water, and you have to know the change in temperature of the water to figure out the heat that's exchanged with the water. This equation is given to you in the data packet, so you don't need to memorize it. Okay, yes, Pancho. Does it matter for now about the negative? Not yet. We're about to get there. So the important thing here is something that a lot of students overlook, and this is what Pancho just brought up, is if you're using the mass of water, and you're using the change temperature of water, and you're using the specific heat capacity of water, then this Q is of water, exactly. And that is not the system. That is the surroundings. And that's what students always forget. So when you calculate this reaction in water, you're solving for the Q of the water, which is equal to the mass of the water times the specific heat of the water times change in temperature of the water. So that heat is being absorbed or released by the water. Okay. Therefore, sorry, what's it, Sophia? Okay. Therefore, how is the heat of the water related to the heat of the reaction? What is it? Well, the value is the same, but it's a sign. The sign's opposite, right? So you can state that the heat of the reaction is the opposite of the heat of the water. Okay. I like keeping that separate. I don't know if in the past that you've kind of learned that Q of the reaction is equal to negative mc delta T, but I think it's a little confusing. I think it's best if you use the equation that's given in your data packet, just realize everything's relative to water, and then just change the sign separately afterwards. Okay. So I like to keep these two concepts separate. Okay. Because if you forget what the sign is and things like that, then again, you're going to be in the wrong direction. Okay. Now, having said that, there is some logic to this, and based on what we talked about with endothermic and exothermic processes, because if you're dealing with water here and the temperature of the water went up, then the water's absorbing heat, right? So if the water's absorbing heat, then this value better be positive, and then the system better be negative. Like, this is kind of one of those ways I've said before, is you logic whether your answer makes sense or not. Mofe. Not exactly. So they are related, which we're going to talk about in a second. So Q is the heat exchange of that specific experiment you did. Yeah, so based on how much water you had and how much reactant you had and things like that, you will make a certain amount of heat for that reaction. But that's not a universal value. What we have to do is we have to make it a universal value relative to an amount of that substance, which is delta H. Yes, Tamor? The specific heat capacity, is that given to us? Yes, it is. Yes, and it's also for water given to you in your constants on the data packet as well. Okay. Now, having said that, bless you, I've seen questions before where literally on the multiple choice where you don't get the data packet, the question literally be, what's the specific heat capacity of water? with the correct units. And so you think that's a gimme, but I think enough kids missed it that they were willing to ask that. So don't just assume. I would still know some of these values. Now, so what Mofe asked is the next part of this, because the Q of the reaction is only specific to the reaction you did. So if you use 50 grams of water versus, well, sorry, if you use 50 grams of reactant versus 100 grams of reactant, you'll get a different Q because you're releasing a different amount of heat. So the important thing here is to then calculate your delta H, which is your Q of the reaction per mole of reactant. So when you're doing a reaction, you have to figure out per mole. And then that way that number is universal, because if we use twice as much reactant, we'll get twice as much heat, but the ratio will still be the same. So delta H is a standard that you will always be able to apply, but your reaction doesn't necessarily apply that. Yes, Ashini, yeah. Oh, okay. So when you're looking at Q of the water, okay, you have to make sure that your sign of your Q of the water makes sense with your values that you're getting. So if the temperature of the water increases, that means your water had to absorb heat. So the Q of your water should be positive. Well, if your water absorbed heat, that means the system had to be releasing heat, which then means your Q of the reaction should be negative. Okay. Now, an aside is this. Again, this is where understanding your units is kind of really important. Sometimes the problem will give you just what's called heat capacity. Okay. And heat capacity is measured in joules or kilojoules per degree Celsius. And so what heat capacity has done has already factored in a constant mass. So heat capacity is when you're doing a calorimetry problem and you're using the same amount of everything every single time, but instead of having to plug that number in every time, they factor that in already. So notice there's no mass here. So the mass of the water doesn't matter because it's already been factored in. Okay, so really important to pay attention to units. You know, I had a lot of kids in the past, they'll see heat capacity and they'll just say, oh, it's MC delta T, so I must multiply by mass and change in temperature. But there's no mass here that you need. So the mass has already been factored into this idea. Yes, Pancho. Well, okay, that's a good question. Some calorimetries don't involve water. Some calorimetries are what are called bomb calorimetries, where you put it in a metal container, you measure how much heat the metal container absorbs. Well, that metal container stays the same every single time. So is there really a point to measuring the metal container every single time? No. So what scientists do is they calculate the heat capacity of the entire metal container, and just that means you've already factored in the mass, so you don't have to worry about it every single trial. So it might be the metal container is 10 joules per degree Celsius. So then you're assuming, okay, that's the whole container. So all I need to do is multiply my change of temperature to figure out how much heat is being exchanged. Okay. Now, all of this is still a very conceptual thing. And we need to talk about understanding really kind of Ashini was implying this as well, is that the IB likes to see if you really understand what calorimetry means. And so let me give you an example of this. And this is something that I kind of devised to kind of help you think about this. I'm going to give you two scenarios. Okay. I'm going to say, let's pretend I am dissolving sodium hydroxide into water and it's releasing heat. So here your delta H is negative because it's releasing heat. Okay. Now, let's say in experiment 1, I put 20 grams of NaOH, bless you, into 100 grams of water. In experiment 2, I put 20 grams of NaOH into 50 grams of water. Okay. So the same reaction, just different kind of scenarios. Okay. Now, having given you these two experiments, there are some values in these experiments that will be the same. And there's some values in the experiment that will be different. And I want you to understand conceptually which ones will be the same, right? Which ones will be different. Okay. So, of what we talked about in calorimetry here, okay, Q, delta T, mass, everything like that, what is a value, and is it the same or different in these scenarios? So give me one value that you think is same or different. Explain. Mofe. Okay, specific capacity of water, is that same or different? Same. So you're going to be both using, in these scenarios, using the specific heat capacity of water. Okay, medicine. Okay, delta T. Now, what is going to be, is delta T going to be different or the same? Why? No, I didn't. You better have a better reason than that. Okay, delta T. Okay, let's go back to delta T because I want you to think about a couple other variables before you think about that. Okay, because understanding the entire system is where this really kind of changes. Okay, delta H. Let's work backwards from what medicine was saying here. Delta H, is delta H the same or different for these reactions? The value of delta H. Why? That's not what delta H is. What is delta H? The heat per mole. Okay, is this the same reaction? Yes. So delta H is the same. This is the same delta H. Okay. Now, yes, Mofe. Q is different. Oh, wait. Why is Q different? Is that's what affecting how much energy is released? No, what is releasing the energy? Sebastian. So therefore Q is going to be what? The same. This is what I'm talking about. That's what's tricky. Because you have the same amount, bless you. We said delta H is the same, right? So that means you'll release the same amount of heat per 1 mole of NaOH. Well, in both these scenarios, we have the same amount of NaOH. So our Q should be the same. No, it does. Because here's the thing. Is the volume of water different or the same, Mofe? It's different. Okay? So your mass of the water is going to be different as well. Okay, think about that equation. Q is equal to mc delta T. You've already said Q is the same. You've already said C is the same. You've already said M is the same. Okay? Well, M is different. I'm sorry, M is different. So therefore, what does delta T have to be? Different. Delta T has to be different here. Because if you're releasing the same amount of heat to different masses of water, the temperature has to be different as well. It is proportional. So which temperature change is going to be higher? With more water or less water? Less water. Okay? So the change in T2 is going to be greater than the change in T1 because you have less water to heat up. So that energy can be used to raise the temperature higher. Okay. Yes. Temperature, correct. No, the final won't be the same. No, it's the maximum temperature change. So, Melvin, we're going to assume with these reactions that we're not going to reach boiling. Like, that's not fair because then you have other factors you have to come in. So, this will be a temperature change within liquid of water that's not reaching boiling. Okay, Chloe. Sure. So, well, okay. Okay, I gave you some of these numbers kind of pretty on purpose to show you this. But so, let's say I'm going to make up the enthalpy of like reaction for this. I don't know what it is. I'm just going to make it up. So, let's say delta H is equal to 1,000 kilojoules per mole. Okay, I'm just making that to prove mathematically this is all true. Okay. Both of these reactions are half a mole of NaOH because molar mass of NaOH is 40 grams. So therefore, the Q of the reaction should be 500 kilojoules per mole. Or, sorry, not per mole, 500 kilojoules. I already factored out the mole. Okay. Now, in experiment one, I would do, well, Q of my reaction is equal to negative Q of my water. Okay, so therefore my Q of the water, sorry, Q of the reaction should be negative. I'm sorry. Let me put a negative here because the reaction is releasing energy. So here, the Q of the water will equal 500 kilojoules. And that equals MC delta T, right? So M is in reaction 100 grams, times 4.18 joules per grams degrees Celsius, times change in T. Okay. And in reaction 2, it would be 500 kilojoules equals 50 grams times 4.18 joules per gram degrees Celsius times this. Any comments? While this shows the correct relationship, if you plug this in and solve for delta T, you're going to get it wrong. Because what is the one thing y'all never pay attention about? Nope. Units. What's wrong with your units here? It's kilojoules and joules. Okay? This is why you write units out. Okay? This is why I'm telling you to write units out because most of y'all will blindly go in there and calculate Q and put equals MC delta T, and you're going to get a delta T that's actually 1,000 times less than it should be. Okay? I'm telling you this, you need to write your units out and make sure you're paying attention. So this is not 500 kilojoules. This is 500,000 joules. Okay? These are numbers are made up. But I'm telling you this right now, you need to start writing your units and get into the habit of that because you will avoid so many mistakes. And you only get one shot at this. It's not like you get to redo any of the questions that you got wrong, like when you're in class and I point out your units are wrong or you divided by the wrong thing. And so this is a safety net. Writing out your units is a big safety net. Okay. And sometimes writing out units just helps you figure out the problem because the constant always has the units that you need. Yes, Tamor. You could. Either way, that would do the same thing. Actually, no. Wait, it would be dividing by 1,000 because you have it as 4.18 joules. You want kilojoules, and kilojoules are less than So careful about that. So that's why I like not messing with that unit so much. Okay, but so although the units are wrong here, Chloe, you could still see that when you solve for everything, your delta T will be half of what your delta T2 will be. Okay. But that's, again, the conceptual part of understanding what calorimetry is. It's not just a plugging numbers into an equation because this is a popular question they ask on the multiple choice. They'll say, which values are different in these two scenarios, or something like that. Okay. So let me propose another scenario, because this is something I spent a lot of time kind of talking about to make sure that students understand this. Okay. 10 grams of NaOH into 100 grams of water. 5 grams of NaOH into 50 grams of water. Okay. Take a second to think about this and use your equations, use your concepts. Think about what's going on in this system here, and take about 30 seconds to a minute and kind of think about this, and then I'm going to ask you, okay? But if you say something, you better have a rationale for your explanation. This is not a guessing game, okay? And I'm not going to tell you whether you're right or wrong until you justify your answer, okay? So have a reason for your concept. Because oftentimes, even if your reasoning is wrong, once you say it out loud, you'll start to realize, and you'll figure out and you'll correct yourself, which is good. Because unfortunately, I won't be there as a little voice in your head while you're taking the test. Okay. 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 Now that we've thought about it a little bit, someone give me one value that is either same or different and a reason. Tamor? Okay. C of H2O is same or different? It's same. Right. So the environment is the same. While that seems to be very obvious, it's still something that you need to understand, because the IB very well could do the reaction in two different environments. And if the C changes, it's harder to see the relationship between other variables if that's not constant. Pancho. Okay, the mass of water, what? The mass of the water is different. Okay. Yeah, right on. Okay. Okay, so, okay, say it again. Okay, so let me establish this. You're saying that delta H is the same. It's the same reaction, right? So delta H is the same. But since you have a different mass, there's a different amount of heat released. Okay. So your Q is also different, right? Okay. The Q of the reaction. Oh, sorry, different. Okay. So the Q of this reaction should be twice as much as this reaction, right, Ashini? Sure. Delta H is the heat exchange per 1 mole of the reaction that's happening. So as long as it's the same reaction, no matter how much you have, you'll get the heat and you'll divide by how much you have, and you'll always get the same proportion per mole. Right. Kind of like the same analogy with like your fuel economy, right? It doesn't matter how far you drive, you'll still spend a proportional amount of gasoline, which will means you get the same ratio. Okay, Pancho. Okay, why is delta T the same? Okay, okay, right. So delta T, sorry, I switched colors there. Delta T is actually the same in the system, because like Pancho said, if you look at the system, reaction 1, Q of 1 is 2 times Q of 2. But the mass of 1 is also 2 times the mass of 2. So if C is the same and the mass and the Q are already proportional to each other, then the temperature has to be the same. Let me write that out in equations to make sure you understand what I'm saying. So Q1 is equal to mass of 1 C delta T1. And Q2 is equal to mass 2 C delta T2. Well, the C's are the same, and Q1 is just like saying 2Q2 is equal to 2 mass 2 times delta T1. Okay, let me say it again. Okay, we've established that the mass of water in the first system is twice as much as the mass in the second system. And we've established that Q is twice as much as well. So all I've done is I've substituted these values into the Q1 reaction here. Now, if I do that and I simplify, guess what I get? Q2 equals M2 times delta T1. So that means delta T1 has to be equal to delta T2 because they're both equal to each other. Yeah, I'm justifying what Pancho said because some people need to see it in equations to prove that. And that's what I'm doing here. Like Chloe said earlier, if you're not sure, it is a good idea to just plug in numbers, and just make up numbers and it'll show the relationship there. But yes, this one's difficult because you see different masses, you see different Qs, so you think, oh, temperature must be different, but it's actually not because the proportion is actually the same. Very tricky. Yes, Anand. If they are proportional in the same proportion of the same reaction, yes. So what Anand said is like, well, what if one system's like 50 or 5 to 50 and the other one's 15 to 150? Yes, it should still be the same proportion. Right. So understanding that concept will help you do this. Yeah. But I'm sure you didn't think about this type of question before today because this is the part of the concept of understanding what's actually happening in calorimetry. So this is how they test because they know, given an equation, that most of y'all are smart enough to be able to plug numbers in. But those students that just plug in numbers don't understand actually what's happening with all these values. And so that's why it's really important that we understand kind of what things are changing, what things aren't. Questions about that? Okay, yeah. Understand the relationship between Q, M, and delta T. Good. Just making sure there's nothing else I need to write here. No, those are the main things that are consistent there. Okay. Questions about that in calorimetry before we move on? Okay. Okay, I don't care. Okay, so the next section. Okay, so, Hess's Law. Hess's Law is the second way to solve for delta H, and it's really important to understand this because I'm going to show you a trick later on that helps you remember kind of how everything else works relative to this. And so Hess's Law is the fundamental thing, and I'll show you tips and tricks about Hess's Law to be able to solve the problem as well. So this isn't just a kind of do this, do this, do this. I found ways that I think are the best ways to solve a Hess's Law problem. Okay, so what does Hess's Law state? Now, you don't need to repeat this. You don't have to define this. You'll never have to say this. So I'm putting this in my own words, okay? So essentially, what we're saying is the sum of reactions determine the delta H of an overall reaction by taking the sum of the individual reactions. Okay, so your job here is to determine the overall delta H because, like I said before, delta H is a state function. It doesn't matter how many reactions I give you and how many delta H's I give you. If all those reactions add up to the same reaction, you will get the same delta H value. Guaranteed. So you might have a system of equations that's 2 equations or a system of equations that's 5 equations, reactions, If they end up being the same overall reaction, they'll get the same delta H. That's the idea of a state function. And that's why Hess's law works. That's why you can make that assumption and you can manipulate reactions. Okay, so you will have to manipulate reactions. Okay, and manipulating reactions means it also manipulates the delta H of the reaction as well. And so I want you to think of it this way. Yes. Oh, yeah, right here. Yeah. Let's say, I'm going to keep it very simple. A yields B plus 50 kilojoules. That's the same thing as saying A yields B, delta H is equal to negative 50 kilojoules. Those two things mean the same thing because it is being produced and it's exothermic. So if the heat is on the right of the reaction, that means the reactants are releasing that heat as a product. So exothermic in both these scenarios. Yes, Aishini? It's in terms of the reactants, yes, if you want to think of it that way, correct. Yes, yes. So let me kind of say what Aishini said again. Yes, if you think of this value in terms of the reactants, so this is of the system. If the system loses 50 kilojoules, then you're assuming the medium that the reaction is happening is absorbing those 50 kilojoules. Okay. Now, when you manipulate a reaction, you manipulate all the terms of the reaction. So, for example, if I want to find out 2A yields 2B, what have I done to the reaction? Multiply by 2. So therefore, essentially what I've done is multiply this by 2, so it becomes 2A yields 2B plus 100. Okay? So therefore, all we've done is we've just changed the delta H of this reaction to minus 100 kilojoules. Okay? Now, let's say we flip the equation. B yields A, the reverse reaction. What have we done to this reaction here? Just reversed it. So what it becomes is B plus 50 kilojoules yields A. So therefore, now what's your delta H? Positive 50. Okay? So in Hess's law, all you're doing is manipulating reactions and you manipulate the delta H along with it. So if you struggle with like multiplying and like dividing and like reversing, sometimes it's just better to write it like this. When you include the delta H in the reaction, some of y'all may like that better because then when you do something to all the other things, you also remember to do it to this. You know, keeping track of all the numbers and keeping track of your information is really important. Okay, that's manipulating reactions. And if you have to have a reaction, you do the same idea. You multiply everything by half, you multiply delta H by half. Okay, so whatever you do to the reaction, you have to do delta H as well. Okay, now, okay, we've talked about this before, but I just want to make sure that we understand what combining reactions is and what that means. We've done it in redox in topic 9. We've done a little bit in equilibrium in topic 7. But let me just make sure we understand what all this means when we say combining reactions. Okay? Species cancel / simplify when on opposite sides. So if you have 2 on one side, 1 on the other side, you really have a net of 1 on the other side. So like, for example, if I say 2A yields B, and then the next reaction is C yields A plus D, what I've done here is I've simplified this to just be A, because there's 2A on this side and 1A on the other side, so the net amount is just 1A on the left side. So species cancel and simplify. Species on the same side are additive. Okay, so if you have 2A and 1A in two separate reactions, like for example, you have like A yields B and then A plus C yields D, then your overall reaction is 2A plus C yields B plus D. Okay, that's the main thing that I want you to take away from this kind of. And then I'm going to show you what Hesss Law does, and I'm going to show you my kind of tips and tricks for Hesss Law that I think will help you be a little bit more linear in your thinking and try to take some of the confusion out of Hess's Law. Okay. Questions about what I've written so far? Okay. Oh, sorry. Here? Here you go. Okay. Now, oh, yeah, sure. Let's go. Right. Let me pull one of these up really quickly. So, okay. Yeah, I will. I was trying to tap on it. Okay. Don't write this down right now because I just want to show you the concepts and you can copy this down later from the notes. But in a Hess's Law problem, you'll always be given the overall reaction and several elementary reactions. Okay. Things you need to know. Okay. And I think they're really important. One, all reactions are typically used. Okay. So I don't believe the IB would ever do a scenario where they give you like an extra reaction somewhere and just kind of throw you off. That they're not trying to trick you. They're just seeing if you can manipulate reactions. So I believe that they will only give you the reactions necessary for it to occur. So if you see a reaction that looks like it's not necessary, it may be because the phase change happened. Like there might be a phase change reaction somewhere that you have to cancel because species only cancel if they're exact same state of matter. So like H2O liquid and H2O gas don't cancel. What, Zana? What do you mean? Well, it has to be the exact same species. Okay. So all reactions are typically used. Okay. Generally, each reaction has a species unique to the overall reaction. And that's what I tell my students to do for this is I say, look at each reaction and find the thing that's unique in this reaction to the overall reaction. Because if you find the thing that's unique in that reaction to the overall reaction, then whatever you do to that equation has to match what's in the overall reaction because that's the only source of that substance. So you have to make your coefficients match. If you do that for every single reaction, everything else will sort itself out. So don't try to make it more complicated than it really needs to be. For example, in this example right here, notice that P4O6 is only in this equation. So based on my information here, whatever I do to this reaction, it has to end up on the other side with a coefficient of 1 because there's no other thing here to cancel it out. So that tells me I need to reverse this reaction. Okay, so I will rewrite the reaction as P4O6 yields P4 plus 3O2. Okay, and I really encourage you to rewrite the reactions out. It helps you cancel things out, helps you visually see it. So every time I do Hess's Law, I generally rewrite the reaction the way I'm manipulating the values. So therefore, this is delta H is equal to 1640.1. And that way I can see, okay, I reversed it, so that the sign of delta H reverses as well. Okay. And then my P4O10 is only in the second reaction, and it's here. So whatever I do to this reaction, it has to end up on the right side with a coefficient of 1, which it already is. So I do nothing to that second reaction. So this is P4 plus 5O2 yields P4O10. And then delta H is equal to negative 2,940.1 kilojoules. Okay. And if you follow that set of guidelines, everything else will sort itself out. I promise. Everything else sorts itself out. Even if there's like O2 and 5 different equations, it'll sort itself out. So look, here, now that these two reactions, everything matches, the P4s cancel, and the O2 simplify, so that it is P4O6 plus 2O2 yields P4O10. That's Hess's law. I know I may make it look simpler than it really is, but we will do practice. Okay. I would say for SL especially, this is one of those things that the IB likes to give you a question on. Like, there's going to be some kind of enthalpy question on this test. I just think it's either going to be calorimetry or some kind of Hess's law or some kind of bond enthalpy. It's one of those things that I think will just be on the SL test. Yes? No. No. You can only do one thing to each reaction. Yes. Oh, sorry. Let me rephrase that. You can only manipulate a reaction once. If that means flipping it and multiplying by 2, you can only do that once. You can't affect that reaction again. So you can only use each reaction once. Okay. Sorry, I'll leave this up and let me pull up another example here that I have in my notes. Okay. Sorry. Did someone say my name? Yes. So let's go ahead and take a kind of 5-minute break between this, and yeah, and we'll do this problem when we get back. So back from break now. Let's go over this again and kind of see how this is applied for another example. So this example here is one that has 3 reactions, and I would probably be willing to bet that no problem on the IB is going to have more than like 4 reactions. I think 3 is usually kind of the optimal amount of reactions that shows you understand what you're doing but not waste so much time on a problem. And so I would say 3 reactions is probably a safe bet here. And so they give you the overall reaction here and states of matter. In this case, because everything matches states of matter, you don't have to worry about that. But if there was a phase change in there, you would have to pay attention to that as well. But so here, again, like I said before, generally every reaction has something that's unique to it that's in the overall reaction. So if you're looking at this problem, you're looking at, okay, well, NO is unique to this reaction, and it is here. And then NH3 is unique to the reaction, and it is here. Okay, and H2O is unique to this reaction, and it is here. Yes, Pancho? No, it is impossible for you to do without knowing the overall reaction. So the only way I could conceivably see that is if the overall reaction were a type of reaction that you should be able to know. Like, let's say they said the overall reaction is the enthalpy of combustion of so-and-so. You should be able to write that reaction out and balance it and then solve it. But I don't think they would have you do that within this problem. Okay, so O2s in different reactions, N2s in different reactions, but it will all sort itself out if you follow the rule of finding the unique thing and making it match. Because you have to remember that, like I said, if this is unique to this reaction, then whatever you do to this has to match this. The NO has to match because there's no other source of NO to cancel out. So whatever you do, it has to match. So in this case, we realize that in this scenario that the NO, what do we have to do to the NO? Multiply by 2 and leave it like that. So the reaction will now become 2N2 plus 2O2 yields 4NO, which then is multiplied this reaction by 2. Yes? Yeah. You add all the values. Yeah. So No, no, no. Sorry. Yes, yeah. Delta H for Hess Law, you always add. There's never a subtract. Now, some of y'all may be thinking about enthalpy of formation or bond enthalpy and stuff like that, and I will clarify that for you when we get there. But in Hess's Law, every Hess's Law problem, you just add all the values because you've manipulated them correctly. Okay. Yes. Possibly. Yeah. They very well could give you fractional reactions, and you just have to kind of work with them the same way. Okay. NH3. What do we have to do to NH3 to make it match the overall equation? Multiply by -2. Flip it and double it. So this becomes 4NH3 yields 2N2 plus 6H2. And you multiply this by -2. Okay. And the last equation, okay? What do we have to do to the last equation? Times 3. So this is 6H2 plus 3O2 yields 6H2O. Okay? And again, if you write all those reactions out and you cancel everything, it will work out. Okay? Because if you look here, the 5O2s are already accounted for. The N2s cancel out. The H2s cancel out. And you're left with whatever is left in the equation there. So let me multiply it really quickly. I've done this problem so many times I should know the answer by now. But yes, wait, what do you mean? Okay, I got negatives. Yeah, this looks right. Negative 1,628.2 kilojoules by adding those three values together. Okay. Yes, Maria. That's a good question. I do not believe they will try to catch you sleeping on these problems. Delta H is generally giving you in kilojoules. No, I get that because Maria asked a very valid question. Like, again, like I said before, the IB likes to manipulate units and see if you're paying attention to that and you're not blindly doing stuff. But I would say it's safe to say that delta H values in the data booklet and in the problem should be given to you in kilojoules per mole. Thank you. Questions about what we did here? Okay, unique things, make the match, everything else will sort itself out. You don't need to worry about O2s, you don't need to worry about H2s, you don't need to worry about N2s. They'll all sort themselves out if you do it this way. Yes, Aishini. Okay, well, let me kind of catch what you're saying there, and it wouldn't be that they all aren't the same. It would be something like in your overall reaction, H2O's a gas, and in the reactions in that you're given, one it's liquid, and then one it's a gas. So that's where you have to make sure, okay, I can solve for how much liquid, but then at the end, I have to make sure it converts into gas. Okay? Yes, correct. Okay? And that brings us up to another conceptual thing they like to ask. Okay? So looking at this reaction here, we figured out that it's negative 1,628.2 kilojoules. The conceptual thing they like to ask is, what would happen to the value of delta H if, sorry, let me correct that, if H2O liquid was produced instead. So in this reaction, delta H is based on the production of gaseous water. Okay. Now the question is, how would this value? You don't have to give me a numerical. It's just a relative thing. What would happen to this value if you made liquid water instead of gaseous water? Okay. So what would happen if you made liquid water instead of gaseous water? Anyone have an idea? Okay. Mohammed. Not bonds. Making intermolecular forces? Okay. What do you mean go down? Well, okay. So Muhammad says it should become less negative. Let me present to you a scenario. Okay. So what we're doing here is we're converting gaseous to liquid, right? And so this reaction here would now be included in the Hess's law because you're converting gas and gas on the right and it cancels to become liquid, okay? Is this process an endothermic reaction or an exothermic reaction, going gas to liquid? Okay, what are happening to the particles? They're slowing down and they're releasing energy. So this is an exothermic reaction. Okay, no. This is where, look, the reason why I brought this up is because a lot of people mix this stuff up. Going from a gas to a liquid means the particles slow down and release energy so they can slow down and become more attracted to each other. Well, because the faster particles are moving, the less they interact with each other. The only way they can interact more with each other is if they slow down. Because then, no, that's because they're colliding with the container more, but they're not interacting with each other more. So this is an exothermic reaction right here. That means the delta H of this reaction is negative. So if this is releasing heat, what will happen to the value of delta H? It'll become more negative. Okay. It gets more negative because going from a gas to liquid is exothermic, so you're releasing even more heat than you did originally. Gas to liquid is exothermic. So this would cause more release of heat than the other reaction. So then when you add a negative to this negative, you get more negative. Yes, because anytime a phase change is happening, the particles have to release or absorb energy so that they can create a phase change. And from going from gas to a liquid, they have to slow down so their intermolecular forces of attraction strengthen, which means the particles are giving off energy. And that ends up being effective here. Yes, Mohammed? Yes. Yes. Okay. Common misconception that it, for some reason, because it feels, just because the temperature is going down, the temperature um, of the surroundings has to be lower than the temperature of the system so that the system can release its heat, right? So um, that's why you think of it as colder, but it's only colder to the surroundings so that the system can release its heat out to the surroundings. Yes, Katrina. Yes, yeah. I would say that if they ask you this question, I would write out the extra equation and then apply because I can't guarantee they'll ask you this way. That's a very good question. They could ask you liquid to gas instead. So I would treat it as an extra Hess law question. This is kind of a higher level thought question that less and less kids get right every year. Okay. So I'm just kind of making sure that you understand what the thinking is there. But yes, like Katrina said, I would write out the equation and then work it out. No, don't just remember it's always more negative because that's not necessarily the concept that we're trying to show. Okay. Now, the reason why I showed you Hess's law first is because you're going to realize that Hess's law applies to every other type of enthalpy calculation. And if you think of it that way, you will have to memorize less than you had to last year. Okay? And so let me give you definitions to apply. So another type of enthalpy is enthalpy of formation, or delta HF. Okay? It is the energy change when I guess we'll do molar enthalpy of formation here. So energy change when 1 mole of substance is formed from standard state elements at standard conditions. Okay. So you need to be familiar with what the definition is and how to write an enthalpy of formation reaction or a formation reaction for a substance. Okay, and that's what the definition tells you. So if you know the definition, you should be able to generate a formation reaction. Okay. The assumption we make for this idea is that standard state elements have a delta H of 0. So that's the assumption we have to make. So therefore, all the energy exchange is based because of the products, not because of the reactants. So we assume that all standard state elements have a delta H of 0. So if I ask for the formation reaction of, I don't know, carbon dioxide, okay, that means I would make 1 mole of carbon dioxide gas from 1 mole of solid carbon and 1 mole of O2 gas. Standard state, so that diatomics apply, everything has to be balanced. And the rule is 1 mole of product. So here you can't have fractional coefficients. You can, because the only rule for this is 1 product coefficient. That's it. So for example, water, I guess liquid or gas, because it could exist in both, would be produced from H2 gas plus 1/2 O2 gas. Of elements. Of elements at 0. Because what you'll realize is that the elements, because all these reactions involve elements as the reactants, those will start canceling out and they will sort themselves out. So everything's relative to these things. Okay. Now, let me add one more in here. Let's say methane, CH4. That would be C solid plus 2H2 gas. And those have delta H values. Let me put variables here. Yes, Eileen. Yes. So, like Eileen's asked, it has to be 1 mole of product. So you write whatever fractional coefficients you need to get 1 mole of product. Okay, so let's go along this concept right here. Okay, let's say delta H of this reaction is X, and delta H of this reaction is Y, and delta H of this reaction is Z. Okay, now let me present to you an overall reaction and see if you can figure out how this works. Okay, let's say my overreaction is this. Okay, let's pretend this is my overall reaction I'm trying to solve for with these enthalpy of formation reactions. Okay, how would you solve this kind of reaction? This is general. What concept are you going to apply to solve for this overall reaction? Hess's law. Hess's law. Okay, so find unique things and manipulate the reactions. Okay, so CO2 is already on the correct side. We leave it alone. H2O, correct side, but multiply by 2. So this becomes 2H2 plus O2 yields 2H2O. So that is now 2Y. Okay. And the last reaction, CH4, needs to be reversed. Right. So CH4 yields C plus 2H2 is negative Z. Okay, so would you agree that the delta H of this reaction is X plus 2Y minus Z? Okay, are we in agreement on that? Okay, what's another way of saying this? What, yeah, products minus reactants. So instead of memorizing products and reactants, all you have to do is think of this, okay? In enthalpy of formation reactions, everything that you want for your Hess's Law problem is on which side? The product side. So any value of delta H that is a product in your overall reaction stays the same sign. And every value that's a reactant in your overall reaction becomes negative. So if you know the definition of enthalpy formation, you don't have to memorize products minus reactants because everything you want is on the product side. So that goes, okay, it's products minus reactants. That's how I teach it. Yes, Ginevra. Yes. If it's because the definition of enthalpy of formation is elements to products, and products are all you care about. So products minus reactants. Okay. So let me say it again because this is the first time a lot of y'all have seen it. Okay. Using enthalpy of formations is just another Hess's law, except that all your reactions are all enthalpy of formations up here. And in all these enthalpy formation reactions, everything you want is on the product side. So like we just did here, we treat it like a Hess's law problem. In our overall reaction, the things that we wanted on the product side, we left the same sign. And what we wanted on the reactant side, we changed the sign. This is why it's products minus reactants. That's the only reason why it's products minus reactants. That's why you learned it that way last year. But this is explaining why that is. Because these stay on the same side and this flips. So do I want you to memorize products minus reactants? No. I want you to go enthalpy of formations mean everything I want is on the product side. The values that I have are for all the products. So therefore, anything that's a reactant in my overall reaction, I have to flip the reaction. So therefore, that's why it's products minus reactants. And you have to multiply by the coefficients as well. I should say that. But that's, yes, Eileen. Sure. A, the definition of enthalpy of formation is elements forming 1 mole of product. Okay? Therefore, if you're using enthalpies of formation, everything you're going to want to look for that's unique, I should say, Eileen, because remember how we said in Hess's Law, everything we want that's unique. Everything that's unique will be on the right side of the enthalpy of formation reaction. So, the things in your overall reaction that are also products, the sign of the delta H's won't change. But if something's a reactant in your overall reaction, the sign will change. Because you'll have to flip this reaction to make it match the overall equation. Like CH4 in this scenario. Does that make sense? It takes a little while to think about this. I know it seems very obvious, but it takes a while to kind of look at that because you haven't ever seen it presented this way before. But so do you agree, Eileen, that reactants in the overall reaction will always be on the product side of enthalpy formation, so we'll need to flip this reaction every time. And that's why it's products minus reactants, because this delta H value will be negative of what you look up in the data package. That's how you know it's minus. Okay. Okay. Anyone else need me to explain that or clarify bits and pieces of it? Okay. Again, minimize what you have to memorize. Okay. Here's what's great about that. Okay. That applies to every type of enthalpy reaction because, for example, okay. Sorry. Shh. Does everyone have this written down? Okay. Let's do this. Same idea for enthalpy of combustion. Yes, Pancho. Yes. What do you mean? I think you need to see how this applies, okay? So, still SO. But, yes. So, we should hopefully be done by 11, and then we'll do HL the rest of the time. Okay, enthalpy of combustion, really quickly. Is delta HC. So, enthalpy of combustion is energy change when 1 mole is combusted, is it combusted, essentially. So an enthalpy of combustion reaction means different rules. It means it's combusting with O2, and you can only make 1 mole of that. So for example, let's say we had C2H4 plus O2 yields CO2 plus H2O. Balancing this would be 2, 2, and 3. Has to be 1 mole here. H2 would be this. And then C2H6 plus O2 would equal 2 CO2 plus 3 H2O and 7 halves O2. Okay, these are all combustion reactions. Give you all a second to write that down. But I'm going to write the overall reaction here. Let's say my overall reaction is the addition of hydrogen to an alkene. C2H4 plus H2 yields C2H6. Let's pretend that's my overall reaction. Okay, I'll give you all a second. You see where this is going, Pancho? So, right, Melvin. So this is explaining again. So where is everything you want now? It's on the reactant side. So guess what? It's reactants minus products. Understand that. Okay. So again, look, again, this is why I'm not a big fan of memorizing stuff, because memorizing, you're essentially putting all your faith in your memory, and I wouldn't gamble on that. And so understanding how things work, much less likely to make a mistake, because you got a coin flip if you just memorize products minus reactions and reactions minus products. You have a coin flip, which a lot of y'all sometimes lose. I hate to tell you. But if you know the definitions, you're doing two things. One, you're being able to recite the definition. Two, you're going to be able to write the reaction. And three, you'll be able to solve a Hess's Law problem. No problem. Yes. No. So that's where the last type of reaction is. So essentially, like, I guess it's not a 50-50, but it's more like a 33-66. And right. Okay, that is true. But I'm going to ask you in 3 months if you know which one's which. And if you don't, it's a coin flip. It's easy to kind of remember that now because it makes sense. But hopefully you'll remember what this reaction is, and you'll tell yourself, everything I want is on the reactant side, so this one must be reactants minus products. Okay. Yes. Just put it up on the counter over here. Okay. Last one for SL. Okay. Bond enthalpy. Okay. Now, bond enthalpy is the energy required to break 1 mole of bonds in the gaseous state. Okay, so how much energy does it take to break 1 mole of bonds in its gaseous state? Okay. And so these values themselves are really only effective when all the substances are what? In a gas, right? Because once you get liquids and solids, you've got other variables that you're not factoring in. So this usually works best only when everything's a gas, okay? Now, what is bond enthalpy, okay? Bond enthalpy is really just breaking a bond. So, for example, let me say this, okay? Breaking a CH bond would look something like this. That's breaking a CH bond. That is what bond enthalpy is. Now, you can't just break one, and that's why when we calculate them, you don't just break one, okay? What do? When you calculate experimentally, you break them all. Because you can't just control breaking one bond in each molecule. So what you do is you break it into this, not H2, 4 H's. Because H2 implies there's new bonds formed. So what you do is you break all 4. And then how do you figure out the bond enthalpy? You divide by 4. Hence why this is called average bond enthalpy. Because it is an average of the energy required to break every single CH bond in a substance. Oh, because you've broken 4 CH bonds here, Zana. No, because the energy to break all 4 of these, we wanted the energy to break one bond. So this is the energy to break 4 bonds. So we want the energy each bond. So yeah, it is. But I want you to understand what that value means. Yes. Correct. So you're going to assume that's for each bond. Yes. But I want you to understand how they calculate that out. Because the IB in multiple choice questions, they'll ask you like which reaction represents the bond enthalpy of CH. This represents the bond enthalpy of CH, or 1/4 of this represents the bond enthalpy of CH. But this equation itself represents breaking 4 bonds. So I want you to make sure everything's in atoms on the product side. Okay. Now, we've established that breaking bonds is what bond enthalpy is. So there are 2 ways you can tackle bond enthalpy. Okay, you can tackle it like a Hess's Law problem, or you can tackle it as an illustrated problem. And so usually what I do is this. Okay, I like to do bond enthalpy a little bit different. You could apply Hess's Law, but I'm going to do this. Okay, I would strongly suggest that anytime you do a bond enthalpy problem, is you draw out all your Lewis structures. Okay, I'm telling you that for a couple of reasons. Okay, one, students think that just by multiplying by the coefficients in the reaction, they get the right number of bonds, and usually that's not the case. Okay. 2, sometimes students forget what type of bond you're breaking, whether it's a double bond or a single bond and things like that. So let's say I have something like CH4 plus 2O2 yields CO2 plus 2H2O. What I do is I draw out every single species. Yes, it takes a little bit of time, but it minimizes your chance of mistakes. So I say, okay, CH4 looks like this. O2 looks like this. CO2 looks like this. And H2O looks like this. And there's 2 H2Os, okay? Because what do students always get wrong? They look at CO2 and they go, I need to look up a C double bond O, which is true, but guess what they forget? There's 2 of them. And then they do water, and they be like, oh, water's OH bond. There's 2 waters, so it's just 2 times OH. No, it's 4. So drawing these out helps minimize your mistakes. That's why I tell you to do it, okay? Too many of y'all will make that mistake if you don't do this, okay? So here, what this is saying is this. We have 4 CH bonds and 2 O double bond O's. Here we have 2 C double bond O's and 4 OH bonds. Now, this is the energy to break all the values you look up are all the energies to break these bonds. Okay? Which side are you actually breaking bonds on? The left side. So if you're breaking bonds here, then the value you look up in your data packet will be correct for that side. Okay? And you make bonds, the value is what? Reversed. So when you make bonds, it's reversed. So the sign of the delta, the bond enthalpy will be negative of that. So guess what? That's why it's reactants minus products. Yes, that's the way to think about it, Zana. Yes. Because look, I want you to avoid making mistakes on this problem because these should be relatively easy points. But I'm telling you this right now, this is a 3-mark problem. And if you get the delta H of the reactants right, that's 1 mark. If you get the delta H of the products right, that's 1 mark. And the answer is 1 mark. So if you mess up if you forget one bond, just one bond in your entire calculation, you've lost 2 out of 3 marks. That's how drastic that is. Okay? And that's what separates a 5 from a 4 or a 6 from a 5, making simple mistakes like that. Not swallowing your pride and writing stuff out, even though you believe you can visually see it in your head. Okay? Trust what's on the paper. Okay. Questions about that? Okay. Trash. 5-minute break. SL, you're dismissed. HL,